Hello everyone, this is Krish Jaiswal, and in this video I'll be talking about what exactly goes under the hood inside of a AI IDE like Cursor. In this entire series, I'll be dissecting the architecture that powers the Cursor's intelligence layer, and by the end of this video, you would be convinced that Cursor is not a VS Code plus AI. It's much more than that, and it's architecturally a lot different than any IDE that is VS Code plus AI. So the agenda of this video is to understand technically how diffs are maintained for multiple source files, how versioning works in Cursor, how checkpoints work in Cursor, and starting off with the understanding of indexes. So in very general sense, if I say that Cursor indexes are code base, and that's a lingo, right? But what does this mean? So what do we mean when we say indexes are code base? The thing is, before understanding any of the terms, we need to understand what an index is. So, what is an index? You must have read books, right? And in all of those books, you can see, after flipping 4 to 5 pages, that there is a set of page that contains only the topic and the page number, subtopic, the page number. Now, what is the benefit of having this kind of an index inside of the books? Yeah, definitely. So, when we say we have this kind of an index, and when we want to look up for something very specific, we don't have to flip through the entire book. We just have to look up here inside of the 5 to 6 pages, and we can flip to the specific page we want to know about. In the same way, technically, indexes are data structures that can map keys to locations inside of a data set, and the entire purpose is to enable fast lookups. Whenever I want something, I don't want to run a O of n lookup. I want things faster than that. I want a O of log n lookup. I want a O of 1 lookup, right? And that too, I don't want to scan the entire data set to find out the relevant portion that I need. And these are the foundations of efficient database queries and code search systems. If I take an example, let's say of a database, we can consider any SQL database, let's say Postgres. The columns on which you want faster lookup, you create a mapping out of them. You create a index out of them. So an index would be considered kind of like a table, with this being column one, this being column two, and the information goes here and here. So let's say if there is a SQL query uh, where I have only this value, I can easily bring out this particular chunk of information without even having to run entire database search, right? So this is what indexes are. The entire purpose is to enable a constant time lookup or a log n lookup instead of a full O of n scan across the entire data set. But here's the point. From people who have known about creating indexes inside of a database, they know how expensive these indexes are. Well, when you say that you want to have a very fast lookup, you can definitely not have an index on disk, right? Because then it entirely kills the purpose of having an index. So where do you have these indexes? You generally have these indexes in more efficient places, let's say RAM or maybe L1 or L2 caches, right? Now these are limited resources. Imagine, I mean, you cannot bring everything up inside of a RAM, right? There is no 1 TB RAM or 10 TB RAM that exists, or you can buy and put all the data inside of the RAM. That's not possible, right? You keep only those which are frequently accessed, and which are like on a fairly large database frequently accessed, and they reside inside of this limited compute. So let's say I have a 100K lines of code inside of a very large code base, and I ask Cursor to index this code base, which means for the indexing of this code base would mean to extract critically important points in my code base and keep it inside of some place, so that when the retrieval system of Cursor wants them, it is basically a very small lookup rather than running lookups inside of the entire code base. So again, not digressing, coming back to, if I say Cursor to index this 100K lines of code, it is not going to save every source file inside of RAM or L1 or L2. And the only reason is these are limited computes. Indexes are expensive. And at the end of the day, Every data change requires a index update. So synchronizing is critical for consistency. So there's a high maintenance cost as well. Now, when all of this is there, the only trade-off why you would want an index is just because you want 100 to 1000 times faster queries. And that's it. That's the only trade-off you could have afforded, right? Let's talk about this in detail. Since we have already understood what an index is, we need to understand now what is the cost of maintaining these indexes. Like, what is the trade-off of getting a 1000 times faster lookup, which is index size can be 20 to 50% of the original data. So it requires a lot of memory, right? For a 1 GB of a code base, indexing like indexes would consume somewhere around 200 to 500 MB alone, which is a storage overhead. Now, what indexes are we talking about? The indexes that we are talking about is about the code base, and code base is tend to change multiple times. The very brute force approach towards this would be to re-index the entire file on each change. So let's say I have a file here, and if I just change a character, I have to re-index this entire file, which brings a latency. So basically, on every keystroke, you cannot re-index the code base, right? So that brings up about like 100 to 500 milliseconds per file change, which is impractical for real use case. Now, I cannot maintain these indexes only on the local space. I have to keep updating the server, the remote server as well, because who knows, that person might delete all their temp files, prefetch files. He might delete even cursor. So the index should still be there, right? And that is the reason why I need to sync from my local machine to the cloud periodically, which means again that whatever change I have here in the index should also be reflected almost immediately on the remote server. Now, this becomes a distributed system problem, and you have to optimize this entire thing to avoid inconsistencies inside of the index. This is the third problem of maintaining an indexes. And again, sending the index updates over a network, re-indexing the entire file, and full index resync can be worth megabytes. So that network latency and data transfer is also a cost that you will have to bear, which correctly comes under the bandwidth. So you might think, like, if so many trade-offs, like if there are so many problems with having a like index, why do people still want to index, and how do they solve these kind of problems while indexing a code base? Well, the solution is something known as Merkle trees. Now, Merkle trees enable a log n change detection instead of complete n full scans over the file. So, which means if I have a code base that is like, let's say, 1000 lines long, I first break it inside of multiple chunks. Let's say I break it inside of like 100 line chunks, right? And now each of these chunk represents a node inside of a Merkle tree. So basically, these chunks are firstly hashed and then they are stored inside of a Merkle tree, right? Now, let's say I make a change inside of chunk 2. Okay. Instead of traversing the entire side of the left tree, I would simply want to re-index this particular chunk. So this solves for the problem of update latency, and since we are not fully re-indexing the like per source file, this also solves for the bandwidth. We'll talk about Merkle trees in the upcoming slides. Let's move forward to understanding how does cursor implement this indexing strategy. So As usual, there is no one result where you can get a very perfect index formed for a code base. So Cursor combines multiple index types across local IDE and cloud services, and their hybrid approach is optimal for different type of query patterns. They keep local indexes for syntax, they and symbol lookups that is like less than 1 millisecond, and cloud indexes for semantic search. Merkle trees, on the other hand, also solve for synchronization. Since I only update a specific section inside of like a specific branch inside of a Merkle tree, it is fairly easier to synchronize it with the previous version of the Merkle tree just by comparing the hashes, right? So Merkle trees basically let cursor track the structural identity of the code. It is some kind of a fingerprint of the entire workspace. So like when a leaf changes or a small code chunk changes, only the ancestor nodes are recalculated or rehashed, which makes some points very clear, which is extremely fast diff checks and diff detection. This is one. Second, the synchronization. The synchronization that has to happen is very minimal here. Third, deduplicating the unchanged regions across sessions is fairly easy inside of Merkle trees, because basically Merkle trees have like for each and every code chunk, it's basically hashed. So let's say if code chunks are hashed, and if there is some kind of similarity between two chunks, their hashes will also reflect that, and then henceforth that won't be added uh, to the cursor's uh, Merkle tree. And this is the exact same reason why GitHub also uses, Git also uses this kind of Merkle tree, but which is applied continuously instead of per commit. Now that we know that Cursor uses multiple index types, let us understand how exactly a code base is indexed by Cursor. So there are two parts of it here. One is on the local IDE end, and the second is on the cloud. Instead of the local IDE, what happens is like this section of the picture represents how a code base is analyzed and how is it indexed more specifically. It all like let's say we have this source code. Now let's say this is written in Java. Since because like Java is my favorite language, so I use Java. So let's say this is written in Java. This Java code base is firstly given to a parser, after which like each and every line of this Java file is lexed. So lexing happens next. Then there is symbol resolution. We'll talk about all of this in detail. And then we finally get a AST. Now, what are the like factors about this AST that makes it different from a source code file? So, firstly, inside of a source code file, if you see, you might have a lot of things. So, there is syntactic sugar inside of a source code file, but inside of an AST, this syntactic sugar does not exist. So, this is like a no fluff thing inside of AST, which AST focuses on maintaining the functionality of the code rather than maintaining its syntax. In case of Java, there is a library called Java Parser that generates the AST for a given source file. Generally speaking, cursor like edit like AI IDEs might want to use tree sitter, which is another um, which is another library for generating ASTs. I talked about AST indexes. I talked about symbol tables here. Oh no, what is a symbol resolution thing here? A symbol table is basically a function or a class name lookup kind of thing. We will talk about this in like exactly in the next slide. We talked about a file index. So maybe there could be an index something like this where we have maybe say src main Java and then some hello.java. against like index of hello.java. So basically keeping a file index in this way. And Merkle tree is for the detection of differences between one source file and the other. So like basically maintaining the versions amongst each source file. What happens inside of the cloud is we have a vector database. Now this vector database is different from any other vector databases or like Pinecone or some other XYZ database. So whatever, like after building the ASD index, it all develops inside of a Merkle tree. That first Merkle tree, the code chunks, they are all like their vector embeddings get generated, and then it is stored inside of a this vector database, which they call turbo buffer. And whenever there is a change inside of this Merkle tree, it just keeps updating that code chunk inside the turbo buffer vector DB. Right? Now let's move forward to understand what are the symbol tables. Symbol tables are nothing but hash maps that associate different identifiers and at different levels. So this level can be functions, this level can be classes, variables, and that too with their location and types. So that there has to be no scanning of the entire source file when you need something. So let's say I write a like I have a file named auth.java. Now auth.java contains three methods, which is authenticate, get user data, and validate token. And it might be inside of like at different line numbers, right? So what I do is I just create an index out of this where I say that this is the authenticate method, and it is present in this particular file at this line number, and this is the entire function. And this is it. This is what symbol tables are. But what does symbol tables optimize for, and where are they located? They are located in the local IDE setup. What do they optimize for? Is basically for instant lookups. So let's say I encounter an error in cursor, like in my code base, I encounter an error and I've asked cursor that this is the stack trace, fix this error. How does cursor know which file to go to, which exact method to look for, to locate all the usages, or to jump to a function or a class, which is like go to definition or find references or update all occurrences? All of these use cases are covered by symbol tables. And since it's a hash map, the retrieval is pretty fast. So the normal lookup time is less than 1 milliseconds for a project with 100k plus symbols. So unlike the language servers that often rebuild the entire state, Cursor uses this kind of an incremental AST mutation, meaning only the modified subtree is reintegrated, only the modified stuffs inside of a symbol table are changed. Which takes us to the next part, which is talking about the inverted indexes for text based search. A lot of time in Cursor, you must have noticed that you know you ask it to fix an error, and it creates some kind of sentences like where is the xyz thing happening, or where is the authentication logic defined in the code base, right? But it does not come out with a lot of results. So Cursor maintains a token to location mapping, so that if a user searches for some kind of a text, it does not have to approximate or just hit vector similarity search, or like something some kind of cosine similarity function to find out the similar content for that particular thing which the user wants to know about. So if the user particularly says that I want to understand what is going on in the authentication logic, cursor should be able to bring out or point out that exact place where the authentication logic is written. Which is why cursor uses the inverted indexes. And this is in the structure that let's say there is a word kind of like add event listener, and it's a list of the file name, the line number, like maybe the line range, like from this particular line to this particular line is the definition of add event listener. So for full text search or grep like queries or like keyword based code search, inverted indexes prove to be very efficient, bringing up like O of 1 for finding a single word, and then O of m to iterate on to matching documents where m is the number of matches you want. This inverted index for full text search or grep like queries is typically under 100 milliseconds for very large code bases, because they basically cursor basically does not have to search through all the files. It specifically knows where this particular method is, or where the following functionality has been implemented in the code base. But what happens during a file change? Nothing. An inverted index entry is updated across all the files, like across the entire table. So for all modified words, this inverted index entry is updated. And this is an incremental update. So it is far more efficient than you think if it is not. But what happens with those code chunks that we talked about maybe in the second or third slide? If you remember the twofold architecture of how Cursor indexes a code base, a part of it also talks about semantic search. Now, Cursor chunks code semantically, often at function levels or class boundaries. So, like these boundaries are defined, and these can be like other boundaries as well. There can be some kind of scope that Cursor looks for to define the semantic boundary. So, it can be a function level thing, method level thing, a class level thing, whatever. But what is the need of chunking here? Well, if you remember, LLMs forget, and that is their like core nature. Forgetting is in their heart, right? So all LLMs have a token limit. Hence, Cursor breaks down the entire 1,000 line of file inside of multiple chunks, and these chunks are mapped into semantic embeddings inside of a very high dimensional space. But what does this enable? This enables a ANN search. So let's say you have a auth1.java, you have another file named auth2.java. Both have a same common method named authenticate. Now, when you ask Cursor that I want to understand where this particular error log is arising from, it will potentially look for both the implementations of the auth function rather than one. But how does Cursor know? What is the specific part that it needs to look for, or what is the specific range of lines it needs to look for to understand where this error originated from? That is brought about by the ANN search. So if you give the context of auth1.java, Cursor will not only restrict it to this particular file, but it will also go and check out auth2.java to investigate whether the following error is arising from this implementation or not. Now, these embeddings map code into a multidimensional space where similarity means meaning. And there is something known as HNSW, which is again an index structure that enables fast ANN search even with millions of vectors, which Cursor uses to find out code samples across, like spread across multiple files. What this enables is it helps us to find the code just by its meaning, not the keywords. Handles synonyms, paraphrasings naturally, and basically this helps in context gathering for the LLMs. Now, this HNSW algorithm is specifically used by Turbo Buffer vector database, which Cursor uses internally. Coming back to the point of how these embeddings work. Now, these code chunks are converted into dense vectors, and these vectors are not 2D, they are not 3D, they are like n-dimensional, like instead of an n-dimensional space. Similar code has similar embeddings, which is like it makes closer, like them closer in the space. And if a query like authentication logic comes in to Cursor, it firstly computes its embeddings and looks for the approximate nearest neighbors. And then it returns the semantically related code, even if the keywords do not match. But there are some trade offs for maintaining these vector indexes, which is embedding generation is expensive, and re embedding on code changes is again very expensive. So the trade offs here are approximate search is not exact, but it is fast. It is fast when we have the when we have the uh, meaning, or when we want to understand the meaning of some code, but we don't know where that code resides inside of the entire code base. And then there is a vector DB storage overhead, which is obvious. Like the higher the number of dimensions you go, the more storage it will require. So if we want to sum up this entire vector indexes for semantic search using an example, if I ask, like if I have a code base and if I ask Cursor, how do we validate the user input? So Cursor first does a vector search. it finds there is a method known as validate email in validators.typescript. It checks, like it sees there is a method known as check password in auth.ts. It also sees that there is something known as sanitize input and utils, and all are semantically connected with each other. And they are closer, like, they are closer in this n-dimensional space. But still, the question is, how are the indexes synchronized? So there are three approaches that Cursor might have thought of when they were doing this. Inside of the local IDE, when I make some kind of changes, it updates the AST, which in turn triggers an update inside the Merkle tree, where the deduplication and all is happening. But the vector DB resides on the cloud, right? The LLMs reside on the cloud. How is it solving the synchronization issue? The biggest engineering nightmare for Cursor might have been the distributed consistency across like 5 index layers. The layers that we discussed was AST, a symbol table, inverted index, then a Merkle tree, and the vector the vector database. Vector database is not exactly an index, but here what we mean with index is to provide better access to the code base rather than running full file searches inside of the code base for any query. So the first approach to solve the synchronization would be to reindex the entire code base every time a single file changes. And we discussed why this is a very brute force approach to not have. Why this is too good to have. Which is because it'll change per keystroke or per change of word, and that would account for 1 to 5 seconds of changes, like 1 to 5 seconds of delay per change, and it has a bandwidth overhead. The approach two is to change the tracking. So basically, track which files have been changed and reindex only those files. But again, the point here is we have to reindex the entire file, and this entire file might be maybe 1,000, 2,000, 3,000 lines for very large code bases. So, what is the best approach? The best approach is to again use the Merkle trees. Since Merkle trees use hash to identify the changed chunks at log n, only the changed chunks are reindexed and synced rather than the entire tree or rather than the entire file. The reason why Merkle trees are optimal is because they are binary trees by default, where each node is again a hash of its child nodes. And a single change to a leaf node would propagate up towards its root. So basically, we can understand that something has been changed inside of this Merkle tree in log n time rather than like a complete scan over that file or the code base. So how does this change detection work? So let's say there is this file, there something has been changed. So this is v1, this becomes v2. So the leaf hash updates for the specific code chunk that has been changed from this file to this file. Then the parent node hash is recalculated. So it has been updated. So I'll just color this up in this way. And this hash propagates up to its root. So these hash propagates up the tree till the root. So it starts with the leaf node and goes this way upward. Now, this becomes really easy for Cursor to compare two Merkle trees rather than comparing two files. Because comparison of two Merkle trees is just about finding the one node, like that one parent node that has been rehashed. So if you identify that this particular node, like or this particular thing has been rehashed, we just need to identify that this node right here was rehashed. And then we could update the embeddings for this particular section of the Merkle tree rather than updating the entire Merkle tree. And then it's simply about traversing the tree to find the changed branches. Now this gives us log n to identify the changed chunks instead of O of n. Uh, and only the changed chunks need reindexing. The bandwidth is reduced by 90% for like very large code bases. And this is even optimal for monorepos where the code base might teach millions of lines of code. In this video, we discussed about symbol tables. We discussed what are indexes, what do we mean by inverted indexes, how vector indexes work, how Merkle trees work, and how multiple index types serve different query patterns, and how Cursor combines them to make local indexes for fast syntax queries and cloud indexes for semantic understanding, and how Merkle trees are being used for efficient synchronization. So in the upcoming video, we'll talk about in detail of what ASTs are, how the tree setup parser works, the Myers difference algorithm, and how all of this comes included with cursor when you try to index a code base. So thanks for watching this video. Wait for the next one. Thank you.